Okay, so what we are going to do today is essentially go over the chapter 10 that deals with populations. And in particular, we're going to look at things like estimating a population proportion. And I'm going to do kind of a little summary of what's going on. And then I'll go in and we'll look at some homework questions and kind of show you how the WebAssign asks you similar kinds of information. Okay, well, let's start with the big picture. We've heard these terms before, but it's useful to go over them. It's very typical that we have a group of people or objects, and we call them the population. And in this particular case, we're interested in a population proportion. So imagine that this population was adult males in the United States of America, right? And the population proportion that we're interested in this story is the percentage, or more likely, the proportion who have been Mexico. Yes, you're just curious, you want to know it. So there are two distinct ways in which we could find this percentage who've been to Mexico, or this proportion. It could be, and let's pretend that we found out that we did a census. Now, a census means you actually find every single adult male in America, and you ask them, have they been to Mexico? And they say yes or no. And the answer, typically we use letter P for it, ends up being, and I'm making this up, 0.32. So that's the proportion. Same thing as 32%, but we tend to like the decimals. So proportion is a decimal or a fraction, and obviously a percentage is a percentage. Well, that's the right answer. End of story. If you could ask everybody whatever it is you're interested in, you'll be able to get the population proportion. 32%, 0.32 of adult males have been to the United States. If you think about it, that's probably not going to happen. Have you any idea, just imagine how much money and time and trouble it would take to find every adult male in America and ask them? Can you imagine? It would be, only governments could afford that kind of money, right? And I ain't got that kind of money. So what do? Well, in the statistics world, what you do is you get a sample. And a sample is, let's say, 200 people. It's a little group. And you ask them, have you ever been to Mexico? And they tell you whatever they tell you. Let's suppose that they tell you that the answer is 0.35. Now, have you noticed that my sample proportion is not the same as the real answer? That seems reasonable, isn't it? Because, you know, the 200 people I picked will be very close to typical adult Americans, but isn't there going to be a little bit of variation? Maybe I get a little bit too many people from Texas. Maybe I get a little too many people who are quite young, right? Whatever it might be. So this is an estimate. And what is it estimating? It's estimating the real answer. So that when we talk about samples and estimating things, what we're really doing is we're finding the sample proportion, and we're hoping that this guy, if we do everything correctly, is going to be close to this one. That seemed like a reasonable compromise to the fact you can't ask everybody. But if you're going to ask some people, at least that's going to be, hopefully, a close estimate. So let's introduce some terminology that you are going to meet up with. The real value for the population proportion, this guy here, this P, is called a parameter. A parameter is any number that comes from a population. In this case, it's a population proportion who've been to Mexico. But in other stories, couldn't it be the average age of all Americans, or the percentage of high school students who smoked marijuana in the last week, or whatever it might be, right? It's some number associated with a population. In this case, it's a population proportion, and it's called a parameter. When you do a sample, this guy here, the one we call p hat, he is called a statistic. And you're going to find in the homework that they give you a story with some numbers in it, and they say to you, what's the parameter and what is the statistic? And you will look and read through the story, and the parameter will be the number that's associated with the population, and the statistic will be the number that's associated with the sample. Now that statistic is estimating this parameter, right? P hat is our best guess estimate of the real value P. Any questions so far? We good? So let's
Could you kind
move.
of, sorry, could you kind of like summarize what the values mean again?
What these two values here mean?
Yeah.
Right. The P value, which is a typical letter that we use for population proportions, is the parameter, that's its name, and it's the true value for an entire population of whatever we're interested in. And P hat, called the statistic, is the equivalent number that you get from a sample. And this statistic, the P hat, is used to estimate the population parameter.
Okay, so p hat is just kind of like a estimated guess or inferred.
Well, it's, yeah, better than a guess, but it is an estimate.
Okay.
Right.
Thank you.
Okay. Well, let's show you now, if I can hit all the right buttons, which is kind of hit and miss for me. I'm going to have to stop sharing and move this over here and share, hopefully, the right page. And it should be this one. Are you all looking at WebAssign page from homework 10A? Right, okay. I think I could maybe make it a little bit bigger, can I? Right. Okay, so this is the kind of question you're going to get from 10A, and at least this is the start of this kind of question. Before I continue, I've got someone said in the chat. Yeah, this will be, I'm assuming I've got your permission to do so, will be put on Canvas, you know, so that if you want to go over and redo a bit, you can do it. Okay, let's look at the first question. In each part of this question, explain whether the proportion that is being described is a sample proportion or a population proportion. Now, they could have phrased that as, is it a statistic or is it a parameter, right? That would have been just another way of phrasing the same question. So here's our three separate stories. In the 2010 US Census, it was found that about 1 in 8 Americans were at least 65 years old at that time. Now, in that sentence, there's a word called census, which is essentially tells you what's going on. Isn't a census you asked everybody in the population? So that means that this number that they've got, the 1 in 8 Americans, it's a population proportion. Right. Question B, a randomly selected group of 500 registered voters. Right, I can stop right there. I don't even need to read the rest. Can you see that that is a randomly selected group? Doesn't that mean that the number you're about to get came from a sample? Right, you didn't ask every single person who's going to vote, right, in that governor's thing. You only essentially that bit there tells me it's a sample. And that word there essentially told me it's a population proportion. Do you see that you should really read the whole question, but when you read a question like that, can you see that there are clues very often right at the start normally that tells you whether you're going to be talking about this information I'm about to give you is a population parameter, right? I've told you everything because I've done a census. Or I've only collected a small group of people to try and estimate something. Oh, you must be talking then that this is a statistic, right? It's a population, it's a sample statistic. Now, C, in a clinical trial done to assess the effectiveness of a new medication for asthma, a satisfactory relief from experience relief was experienced by 56% of the people. I've got a little window that's covering up half my writing. There we go. And N equals 60. Okay, is that a sample? In which case we're going to be looking at a sample proportion, or is that a population value? What's the right answer for that one?
A sample.
Right, what was you correct? What was the clues for you?
Well, I think like 70 participants.
Yeah. So when you're looking at only asking a small number of people, which clearly isn't everybody, but you agree there's millions of people with asthma. I happen to have asthma, for instance, right? There's millions of them, but they're only looking at a small group. So if they see a small group, you know you're looking at a sample. If the story is we asked everybody, right, then you know that you're looking at a population. Right? Small group, sample, everybody, population. And there are different ways in which that can be phrased. In question 2, a survey is done to estimate the proportion of adults who think that texting while walking across an intersection in the crosswalk should be illegal. Oh, like you're not allowed to text and drive, so I guess you shouldn't be able to cross roads and text. Maybe that's basically. In a survey, 53% of a randomly selected sample of over 1,000 said that it should be illegal. So we are being asked some questions about that story. Now it says, what is the population of interest? And they give us 5 choices.
Hey, Professor.
Yes.
Do you mind scrolling down so we can see the question you're talking about?
I have scrolled down. Can you not see it?
Oh,
It
I
says
cannot.
question.
Sorry.
It says question 2A at the top. Can
I'm
you see
only
it,
on
Tommy?
one.
Yeah, it's only showing one, and the key is also on, so that it's going to show the solutions next to each one.
Okay, let's figure out what the heck's going on here. And I will try that one again. It's not very helpful to see the answer. Well, in this case, I don't think it's very helpful. Right. I think my problem is I've got my windows in the wrong place. And so you're saying, okay, where's share? Ah, make that go away. Where is share? Come on. I know you're here somewhere. I've lost my ability to share. That's strange. Okay. Excuse me while I have a short mental breakdown here. Somewhere in all the windows I've opened and closed, I've managed to close the one that allows me to share things. So I'm going to leave the main and come back and hopefully get that share button, because I can't think of any other way to do it. And I am going to put Emma in charge of the class while I do that. Yay, I'm back. Okay, I've now got my share button. Are you looking at question 2 now?
Yes.
Okay, whatever was doing that, I don't know what it was, but it's a pain in the butt and it's gone away. Okay, so the question we had here in question 2 was concerning a survey was done. They asked 1,000 odd people and 53% of them said should make it illegal. And the question is, what is the population of interest? Well, when you're looking at this, you have to be careful about not getting too caught up with the details, you know, that can't see the forest for the trees. And the key to deciding what the population here is right at the start. A survey is done to estimate the proportion of US adults. So it's that one. Does that make sense? Now, if the question is said, a survey was done of people who use cell phones to text, then I would have probably chosen a different answer, right? Or if it said a survey of teenagers, then I would have changed my population accordingly, right? So the people you're asking your sample from come from a population, and that's kind of how you figure out what your population is. Now it says, what is the population parameter of interest? Well, if we read on to the next bit, isn't it, think texting while walking across a crosswalk should be illegal, right? So we go through this sentence and we look for the proportion of adults who think walking across the intersection should be illegal. And I believe, if I've read it correctly, it's the second one. That seem reasonable? Yeah. Now, what is the sample here? Now, if we look at the top here, the sample is that. So the sample is that. So far, so good. Now, the last one is a number or a fraction. And it says, what is the value of the sample statistic? Well, 53%. Now, here is something that just annoys the heck out of me, and I bet you it annoys the heck out of you. You could type in 53%, which is correct. Isn't that the answer that they got from their sample? And it tells you you're wrong. Can someone tell me what the very slight clue to why 0.53 is what they would take and not 53%?
Have you ever programmed?
I have actually, yes. But I'm not the one who wrote this, so I'm not going to be blamed for it. What's the clue? Because what's going to happen is you're going to do some questions and you're 99.9% sure you're right, but it keeps telling you you're wrong, and you start doubting yourself. And why is it 0.53 and not 53%? How do I know which? It may take, sometimes it takes both, but in this case, I suspect it doesn't.
Because it asks for the value, not the percentage.
That would be the biggest clue. Secondly, normally when they want a percent, don't they put a little percentage sign outside the box so you don't need to type it? So if I don't see a percentage sign outside the box, I'm just going to stick in the decimal. Now, other things can happen, not in this question, but do you know when you do 84 people out of 742, you get a ridiculously big decimal? Shouldn't you also make sure that you read carefully about how many decimal places they want you to round your answer off to? Because some people have sent me emails saying, I think I got this right, but why is it telling me it's wrong? And I have to say, they wanted it to 3 decimal places, not 2. You know, you just rounded off differently. I think it's even weird if you go the other way. If you write down it correct to 4 decimal places, which is actually more accurate, but it wanted 3, I think it will also tell you that you're wrong. So just, you know, and I'm guilty of it as everyone else is, be careful when you read it to make sure that it's a decimal or a percentage they're looking for, and what kind of rounding off they might be doing. So I'm now going to hopefully return to our screen. Here we go. And we're going to look at what are called confidence intervals, which is actually what most of this chapter is going to deal with. Well, let's just imagine what the problem is if you were looking at a realistic situation. Right, back to this one. I would like to know what percentage of adult males have been to Mexico. And I collected a sample of 200 adults, a nice random sample, and the answer I got is 0.35. It would be nice if we could just generate a little bit more information. Like, is that a good answer? Is that a good estimate, right? In other words, will we be pretty sure that the real answer's dead close to 0.35? Or is it a very vague estimate? Well, you might say, well, what do you mean by that? Can you imagine I only asked 20 Americans that question? Would you be very worried about betting your house that that number was close to the right answer? Isn't there a really good chance it could be screwed up massively? Because with 20 people in Qatar. On the other hand, if I did 20,000 people, right, it was a good random sample, and I did 20,000 people, wouldn't you feel much more confident about the estimate? Right? So what we have here is, in statistics, we figure out a way to try and factor in essentially the sample size. How do we use the fact that big sample size give you much more accurate answers than small sample sizes, right, in typical? And what we do is we create a thing called a confidence interval. So we're going to use that guy, the 0.35, to create one of typically 3, although the book has a 4th one I don't like. And these confidence intervals are 90% confidence interval, 95% confidence interval, and the 99% confidence interval. And we can calculate these confidence intervals if all you tell me is the sample size and what our estimate, our p-hat is. Right, just with those 2 numbers and nothing else, we can create what's called a 90, a 95, or a 99% confidence interval. So I'll be doing that question in a minute, but I'm going to do it kind of vaguely right now. Can you imagine that we had an interval from here to here, and this is my 90% confidence interval, right? And what this is going to say is that we believe that the right answer, right, this number here, we're 90% sure that somewhere in that interval, this number is. Now, if I wanted to be 95% confidence interval, in other words, I want to be 95% sure, do you see that my interval would have to be just a little bit bigger, wouldn't it? To have more stuff in it, to be 95% sure that somewhere between here and here, the right answer lives. And lastly, if I want to do a 99% confidence interval, wouldn't my answer have to be even bigger? So as you make the confidence interval percentage larger, if you want to be 99.999% sure, can you imagine that your interval would be extremely huge? It would be ridiculously big and probably not very useful. I could, for instance, tell you that I'm 100% sure, right? 100% confidence interval that the percentage of adult males who've been to Mexico is somewhere between 0 and 100%. It's almost like a joke, isn't it? Well, you're right. It is somewhere between 0 and 100. But isn't that going to be the same answer for everything that involves percentages? So we have to do a compromise, right? We can't be 100% sure. We can be 90% or 95 or 99. And these are kind of fixed values that, you know, the statistics world has said, yeah, these are pretty good numbers. How do we calculate them then? How do we physically come up with these confidence intervals? Well, we need to find a guy that you've met called the standard error. And his formula, SE of p hat, is given by the square root of p hat, 1 take away p hat over n. So if you're ever being asked, tell me what the standard error for this sample is, right? So if they give you a story and they ask 200 people and the answer came out as 0.35, the standard error is this guy here. From the previous last week stuff, the standard error is essentially the standard deviation of the sampling distribution, if you want to know its full title. But it's really just a number that's going to help us create one of these confidence intervals. So in this particular one, p hat is 0.35. 1 minus p hat, well, if you take 1 away from that, or that away from 1, you get 0.65. And in this case, you divide by a sample size of 200. So I go and I type in the square root of 0.35 multiplied by 0.65 and divided by 200. And let's assume that the question was going to be to 3 decimal places. So do you see how that last 37 becomes a 4? And that is your standard error. That is the first thing you would do if you were going to calculate one of these confidence intervals by hand. I'm just going to write these two numbers down again, because I'm going to move a piece of paper over. So let's show you the formula for the 90% confidence interval. Its formula is p hat, the sample statistic, plus or minus 1.645 times the standard error p hat. Now you might be curious, from where did this 1.645 come from? It is a fixed number. That's the number that makes a 90% confidence interval happen. You just memorize it, you write it down somewhere. If you do it enough times, you just get used to using it. Now, if you want to do a 95% confidence interval, it's p hat plus or minus 1.96 times the standard error. Do you notice the only difference is the magic number that you multiply the standard error by? And have you noticed that that number is bigger than this one? Can you see why that makes the interval grow larger? Can you see that multiplying by a bigger number makes this a bigger answer? And the last one is 99% confidence interval. And it's p hat plus or minus 2.58 times the standard error p hat. And can you see that for a 99% confidence interval, this number becomes even bigger, which kind of makes sense, right? 90, 95, 99. Okay, which one of those three do you want me to do just as a calculation to show you what it looks like? Anybody got a preference? Do you want a 90, a 95, or a 99?
Could you do 99?
Let's go for it then. So just do that little fella here. A 99% confidence interval. It's going to be p hat, which is the sample statistic, 0.35, plus or minus 2.58 times the standard error, 0.034. And that's going to be 0.35 plus or minus, I'll bring my calculator into play now. So it's going to be 2.58 multiplied by 0.034. And the answer we get is 0.08. I decided, didn't I, that it was going to be a 3 decimal place question. So I'm rounding it off to 3 decimal places. You comfortable with the rounding off 0.088? Now, you take this number and you subtract that. You take this number and you add that. I think in the WebAssign, they're called something like the lower value and the upper value. Right. The lower value is 0.35. Take away this number. And the upper value is what you get when you add this number. And we have 0.35 take away 0.088. And the answer I get here is 0.262. So that's the lower value. If you like, the lower estimate, right? So the percentage of Americans who've been to Canada might have been as low as 26% roughly. And then if I go 0.35 and I add 0.088, we get the upper value, which is, in this case, is 0.438. Now, as an interval, our estimate for the real value is somewhere in that range. Agreed? Now, let's see if that was any good. Hey, that was pretty good, wasn't it? Isn't 32 somewhere in this range? Right, now when we say we're 99% confident, all we're saying is that we're 99% sure that the real answer is somewhere in that interval. It could be as low as 27%. It could be as high as 43%. There is no one value is any better or worse than the other. So that 35% isn't any better than the 27% or the 43, right? Any of those numbers or any of the ones in between here and here, they're all equally likely to be the real answer. So what we've got here is a way of expressing how comfortable we are with our estimate. Can you see that's a much better way of telling someone where the answer is? I'm 99% sure it's somewhere in this region. Rather than, that's my estimate. Can't tell you much more. Could be a good one, could be a horrible one, right? Now, let's introduce you to some terms. This number here, the one you get by multiplying these two guys together, this guy is called the margin of error. And that's its name. It's called the margin of error. Any questions about how I created that? Anything that you're not sure about you'd like me to explain?
Can one of the results be negative?
Theoretically, you could get this number so big that the difference generates a negative number, right? But we know you can't get negative percentages of people who've been to Mexico. So in practice, what you would do is you just make that the number 0. Right, just common sense. You can't have -5% people going to anywhere, right? Or -5% people voting, or percentages in populations have to be positive numbers, right? The worst you could ever get is nobody did whatever it was, right? Well, that's 0. You can never get negative in real life, but you could get a negative in this calculation. So can you pretend that a different story, this number was negative 0.03 and it went all the way up to 0.07, right? Just for argument's sake, right? What you would do is you would call that 0 to 0.07. And that is not a mathematical rounding off, isn't it? Just a common sense thing that you know your answer can't be negative. Now, in that same vein, couldn't you in a different world get an answer where this guy up here is bigger than 100%? Right. Could happen. So what do you think you do? Well, you just make it 1, right? You take your answer and then you tweak it. Now, hopefully you don't have to do that because that's kind of annoying when it happens, but it could. You just make negative numbers 0, and anything bigger than 1, you just make it 1. Any other questions? That was a good question. I like that. So far, so good. Right. Now, you know the book's going to do things in all sorts of ways. So I think it's a good idea for me just to go in and try not to lose my share button. Learned that mistake. I think this is good. Are you looking at question 3 now? Okay, so what is the likelihood that a 90% confidence interval will not cover the true population value? What would the answer be?
So I'm going to go ahead and go
1%.
Sure about the number 1? 90% confidence interval? What percentage?
Sorry, I'm
Well,
reading
not.
my question, not yours.
Oh, your question, okay. In your question, it was 99, right? In my question, it's 10%, okay? And if you think about it, if there's a 90% chance it's in the interval, isn't there a 10% chance it's not? If it was a 95% confidence interval, wouldn't there be a 5% chance that it wasn't in the interval? And the one James was doing in his homework was a 99% confidence interval, I'm assuming. And so there's a 1% chance it's not in it. So when you do a confidence interval, don't think you've got the answer. It's never 100% sure. Isn't there a bit of a chance you just got unlucky and your interval's no good, right? The real answer's just not there. It's outside the interval somewhere else. Okay, let's look at this story. A certain poll surveyed a random sample of 431 teenagers. One question that they were asked was, how strict are your parents compared to your friends? The choices that they could choose were more strict, less strict, or about the same. The choice more strict was selected 169 of the teenagers. And then it goes on and says, suppose that in fact the true population percentage who think that their children is more strict is 40%. Okay, so there's a lot of information here. So if you took a new sample of 431 teenagers and you asked them the same question, right, which of the following would be true? Right. Would you expect the number that you selected would be 169 again? If you asked, could be, but would, so it could be, right? Would you expect it could not be 169? Or it would be 169? So there's your three choices. I think the way it was answered to me, you were saying that one. Would you agree that is the three choices? If you choose another sample of the same amount, it could be 169. It's not the same as would be. Wouldn't that mean it would be exactly 169 every time, which is not feasible? So just the English language, a could be is a much better answer. And why am I kicking that one out? Well, you know, sometimes you do get the same answer twice, don't you? If you do enough samples, it could happen, right? It could be the same number again. Okay, here's one to do with populations again. Suppose that a survey is done to estimate the proportion of US adults. I've done that one. I'm not doing that again. Here is our creation, partly anyway, of a confidence interval. Now this one's not quite as hard as one I did. This one, pretty much what you need to know is in front of you, so we just have to find it. In a survey, 41% of random selected sample of adult Americans said they did not get enough sleep. The margin of error for a 95% confidence interval was reported to be 3.5%. Do you see in this question, you don't need to calculate standard error. You don't need to multiply by anything. Haven't they just told you what the number that's going to be plus and minus is? It's going to be 3.5%. So if I take 41 and subtract the margin of error and 41 and add the margin of error, I should be good to go. So that'll be 37.5, I think. And you see the little percentage? So I know I'm using that, not the decimal. And up here, if I add it, I think it's 44.5. So we would, based on that sample, we are 95% confident somewhere between this number and that number is the true answer for all American adults. So with 95% confidence, we can say that the population of American adults, so that is between 37.5% and 44.5. And then they finish with what I like this question, because the first time I looked at it, I got it wrong. And I like questions that catch me. Do you think this sample could be used to estimate the percentage of college students who think they don't get enough sleep? Right, you get 4 choices, dot, 1, 2, 3, or 4. Which one is actually the correct answer? Well, I have no idea what that is, but I'm killing it right now. Right. Anybody want to volunteer and answer that one before I tell you? Which one of those 4? Is that a yes or a no? At least you should be able to go for that.
I think it's the violating one.
It is the violating one, you're right, which is no. You couldn't use that interval to try and estimate what college students do. And you might say, well, why not? Well, this sample was American adults, right? All American adults. College students are a subgroup of that. Isn't there a possibility that they may not be the same as the general population, right? They're younger and therefore they can do with more or less sleep, who knows what. If you are going to do any kind of confidence interval, you have to make sure that your sample is a fair representation of the population. You can screw that up the other way. Suppose I wanted to know the percentage of adult Americans who, thought they weren't getting enough sleep, but the only people I asked were 18 to 20-year-olds. Can you see that that sample isn't a fair representation of all American adults, right? So your sample has to be what we call a fair representation. So that was a good question. I get caught out. Does anybody know what this is a fluke if you can get it, what I thought the correct answer was the first time I did it? Yeah. I didn't read the question carefully enough and I picked the no up there. And I just didn't notice fulfilling and violating. Now, they talk about that, but we haven't mentioned it. So let me zoom out for a minute and talk about these fundamental rules that you really should obey when you're doing samples. Right, first rule. The sample should be big enough. Would you agree it would make sense that you couldn't do a sample by just asking one person? Right? Not a good idea. Or even 2 people, still not a good idea. So what are the rules for what is big enough? Well, they do actually have a test. N p hat should be bigger than 10. I guess equals 2 in some textbooks. And N 1 minus p hat should always be bigger than or equal to 10. So if you're talking about a sample, the N times the p hat, and you can turn that into English. There must be at least 10 people who said yes and no to whatever your question is, right? Because these questions are, they ask you something, you say yes or you say no, right? They're binary. There are only two choices. So if I asked 1,000 people, have you ever seen an alien? And the answer was 9 people said yes and all the others said no, I couldn't do a confidence interval because 9 yeses is too small. Try a different one. Can you imagine that you're interested in a very, very rare form of cancer? And you took a sample of 1,000 people and only 4 of them had that cancer. Do you see that would not be a big enough yes answer to allow you to do a confidence interval for what percentage of Americans have this very rare cancer, right? So that's your first one, right? Sample should be big enough. That's how you tell. 2, should be a fair and representative sample. If I'm interested in the percentage of adult males who've been to Mexico, shouldn't my sample only have adult males in America, right? I shouldn't go over to France and ask them, right? My sample shouldn't contain Frenchmen, right? My sample shouldn't actually contain any women either. Agreed? If my question is the population should be adult males in America, that's the only place my sample should come from. Now, the fair part kicks in with, don't just ask 18 to 20-year-olds, have you been to Mexico? Shouldn't you ask 18, 20s and 55-year-olds and everything else in between? Right, that's the fair part, right? Fair and representative. And the third one is independent. When you pick people from your sample, every single person that you choose should be independent of anybody else. So how can you screw that up? Can you imagine that to save time and money, you went and asked everybody in a family, all the adults in your family, then all the adults in your friend's family? Can you see that those adults are not independent? If your dad's been to Mexico, isn't there a good chance that maybe your big brother has been to Mexico because he went with him, right? Or if your Uncle Joe had been somewhere, isn't there a good chance that your cousin Fred could have gone there as well? So do you see that you can't pick a sample that's not independent? It just basically means everybody is random. Nobody has any connection with anybody else. That way the independence works really well. And there is a fourth one, which we don't really spend a lot of time on because we assume that it is true. Do you know what the fourth one is? And that's, was the question that you asked in an unbiased way? Now, for the Mexico question, I can't think of a biased way of asking, have you ever been to Mexico? So that one's probably guaranteed to be safe. But can you imagine there are some questions that you could phrase in a way that was biased? How about you're interested in, are you in favor of abortion, right? I could ask that two quite distinctly biased ways. Are you in favor of killing unborn children? And I'm asking, are you in favor of abortion? But would you agree that that is a very biased way of asking it? I could also say, are you in favor of a woman's right to choose? Can you imagine that that's also got its bias? So we tend to assume that you don't try and fix the answer by asking the question in a very bad way. But sample size is worth looking at. Fair and representative group, that's very useful. And independent, less so, because we tend to assume that your sample is pretty random, so that doesn't happen. So let's return now back to our homework. So a question given on MSN.com website asked, how good are you at math? And they got 324,000 people responded, and 18% of them said they were very good at math. Can the method of this chapter, right, of this particular way of doing it, be used to find a 90% confidence interval? The answer is no. And the choices are .1, .2, or .4. Why is it not a good sample?
Because people can answer whatever they want.
That's true. But does any of our four, the three
One
choices?
you're on.
Say again?
So the one you're on, because the fundamental rule can't be inferred from that.
Yes. This sample is a self-selected sample, right?
I don't like
People-
that question though.
I don't blame you, but that's what it is. Yeah, this particular question, this sample is only from people who decided that they were going to join in, right? They decided to answer the questions. Self-selected sample is one of the names you could give to that type of sample. Very dangerous. Phone-in samples, when they used to use phones a lot. Yeah, phone this number if you agree, and phone that other number if you disagree. You know, the ones you sometimes see on television when they want you to voice your political opinion about something. The reason that it's bad is that it's not a fair representation of every American. This particular one isn't the only Americans who go to MSN.com. I don't know if they're better or worse at math than the rest of the population, but they're different. I'll let you play with that one. And in here, oh, here width ones. We talked about this. Explain whether the width of a confidence interval would increase, decrease, or remain the same. So the width would be, you know, from the start to the finish, right? How big is the number from the beginning to the end? So if you visualize a line, is it like that? Is it like that? Is it like that, right? Now, if you went from a 95 to a 99, increasing it will increase the width. Would you agree? 95, 99. If you went from 95 to down to 90, what would that do? Well, that would decrease the width. Oops, like that. And here's another question similar to that. And that is the end of 10A, which is pretty good. And if you give me a few moments, we'll kick into 10B. Right, I don't know. Can you see 10B or will I have to go out and in? Can you see 10B?
Yeah.
You can. Oh, that was good. Now, we've done one calculation, the one about Mexico, where we calculated the confidence interval, a 99 it was when we did it. And this section basically gets us to do the same thing. There's going to be a question, we have a lot of information in it, and we are going to create confidence intervals, right? And you'll notice that it asks sometimes for standard error, sometimes it'll ask for the value of the margin of error. And then it's typically, it might even finish with a little, which one of these 4 or 5 choices is the right one to interpret. What makes this a little bit different is that you can also use SALT to do the same thing that I did by hand. So let me just jump out and in for a minute and explain why I did what I did the first time. Right, can you remember this was our calculation that we used to do a 99% confidence interval for the percentage of Americans who have been to Mexico. So what I want you to imagine is that here is our formula, and this is how we got our answer. But you can imagine that it could be quite time consuming if you had to do this kind of calculation every time. So what SALT does is it basically does everything that I've done, but it does it for you. So I'm going to show you now how you can use SALT to do that. Right? How do you come up with this interval? Right? A 90, a 95, whatever you want, by just pressing or telling it the relevant information, right? And we just have to get a little bit used to how it wants the information. Apart from that, it is good. But I feel it was necessary to show you this. Because I don't want you to just think, oh, you just hit some buttons in this program called SALT and some numbers appear and you write them down and that's the answer. I really don't know what I was doing because I only hit buttons and I typed in some numbers and it done stuff, right? So this is what it's doing. But it's going to save us a lot of time and grief, isn't it, if we can let SALT take over the heavy lifting, right? All the number crunching. But at least you know once in your life, hopefully more than once, what to do. Right, so I'm now going to look at this question and use SALT on it. So I have to write down things, so bear with me. A poll of 1,000 Americans. So you'll see me writing down the information I'm going to use. Since it's a poll of 1,000 Americans, N is 1,000, okay? And it's conducted by telephone, and it was designed to measure beliefs about the end of the world, apocalyptic predictions. One of the results reported that 63% of the sample said that they believed the world was going to come to an end according to the New Testament. And it says round all your answers to 3 decimal places. So they have just told me that p hat is going to be 0.63. That's fine. And just to remind myself, everything is 3 decimal places. And we would like to calculate standard error. And then, right after that, a 95% confidence interval. Now we can do this 2 ways. I'm going to do another one by hand, and then we're going to go in and we're going to show you how you do it with SALT, right? Just so you can see them. And I should warn you a little bit here. There might be some rounding off errors. In other words, my answers might be a little bit different on the last digit, right? And that's fine. It's rounding off, things like that happen. Okay. A standard error is the square root of p hat 1 minus p hat over n. In this case, 63.37 over 1,000. So I get my calculator. I'll do the square root. Well, 0.63 times 0.37 divided by 1,000. And to 3 decimal places, 0.015. There we go. Are we okay about the formula that I used and how I got that answer? Comfortable? Okay. Now, the 95% confidence interval is going to be this middle one, right? So the 95% confidence interval is going to be p hat plus or minus 1.96 times the standard error. So it's going to be 0.63 plus or minus 1.96 times 0.015. So that's going to be 0.63 plus or minus 1.96 times 0.015. And the answer I get is 0.029. Now, they didn't ask it in this question, but can you imagine in another homework question, they might have had, what's the margin of error? And that's the guy you're going to write down, right? Standard error. If they asked you, they didn't this time, but margin of error. Right, so I should be able to get my intervals up right now. That guy, take away that guy. So 0.63, take away 0.029. And the answer I get is 0.601. And then 0.63, add 0.029. And the answer I get here is 0.659. Right, are we comfortable about the calculation to generate this 95% confidence interval? Are we good? Right, now let's show you how you can do the same thing on salt. Let's try that again. I had the wrong button. Okay, you hit the use salt button. What the heck is it done? Okay. Can you see the salt window? Right. First thing you're going to do is make sure that this guy here says 1 sample proportion. Okay. Now, our first little problem. It doesn't have a box for me to put p hat in, right? P hat was 0.63. Right. All it has is number of successes, number of trials. Now, in this story, it was 63% out of 1,000, right? Now, 63% of 1,000 is 630 out of 1,000. Do you see I had to figure that out because it wasn't in the story? So can you imagine in another story, they had a sample of 200 kids and 25% of them said they hated chocolate. Right, wouldn't I have to find 25% of 200 kids, which is 50 kids, and say 50 successes out of 200 kids? Right, so you got to do the yeses out of the sample size of 1,000. Right, so 63% here ends up being that. Now you go down and you hit the confidence interval button, and you change that number to whatever the confidence interval needs to be. Well, it's exactly what I do want it to be, right? But can you imagine maybe the next time it's 90 or the next time it's 99, right? So you change it to whatever the question was. So that's 95. And then all I do is generate the results. And can you see the p hat is 0.63? Can you see the standard error? 0.0152. Wasn't that exactly the same guy I got if you round it off? Now, where is the interval? Lower limit, upper limit. Now, if you round these guys off to 3 decimal places, do you see that that guy says 600? And this guy here would have said 660. Right? Now, do you notice that is 1 digit off from the answer I got? I would have said 601, and they will say that guy. So you might say, what went wrong? Nothing really went wrong. Wasn't I rounding off to 3 decimal places all the way through? What the software was doing is it wasn't rounding off anything. So do you see, by not rounding off, right, doing your answers to whatever it is, 8 decimal places, that you're going to maybe be a little bit out at the end? It's not a problem. I've told WebAssign to allow wiggle room. So when you type in 601 and 659, you'll be fine. If you use their numbers, which are what, 600 and 660, you'll be fine, right? So that's just, you know, that's just the issue of rounding off. Sometimes it won't harm. Sometimes, you know, the rounding off doesn't cause any problem. Sometimes the last digit's 2 out or 3 out. It's okay. Are you comfortable about how to use salt to do a confidence interval? You good? Right, let's make up one. Is this just me, or is the left-hand side of that window went weird on you? It's missing.
Yeah, it's missing.
What the heck happened? Go. Full window. Full window. Okay, you're just going to be awkward, aren't you? Okay, I'm going to move it to a different screen. I want to see the whole thing. Okay, are you, maybe you're not. Try that again. Right, are you seeing a full version of Salt now?
Yes.
Yay, okay, good. Right, I'm going to pretend different questions. Suppose I asked, well, let's do that story with the Mexican ones that I just did, right? Now, you remember in the Mexican one, it was what, 35%, and what was the sample? Find my original data. It was 200, right? 200 people we asked, and 35%. Okay, 35%, 200 people ends up being 70 out of 200. How do I do that? Find 35% of 200 and you get 70. 70 out of 200. Right, now, the confidence interval that we did was 99, wasn't it? And then just generate the results. And they have 263 and I had 262, and they have 437 and I had 438. You see, it's pretty much the same numbers, little wiggle room at the end caused by rounding off. Okay. Let's pretend I did another one. I went and asked 200 OC students, do you like Pepsi Cola? Is that your favorite cola? Right? And 42 of them said yes. Right? So 42 out of 200 OC students liked it. And I'd like to know what a 90% confidence interval for all OC students would be. So success, trials, confidence interval, generate result. And somewhere between what? 0.163 and 275. If you want to know p-hat, 21%. You want to know the standard error? It's that guy there. The good news is virtually every single question that involves a confidence interval is just going to be figure out that number, figure out the sample, and change that to one of the confidence intervals. And then all the numbers, virtually all the numbers, are going to be over here on the right-hand side. Okay, let's try another one now. Just go into question 2. Just this one. Suppose you took a random sample of 300 people. 56 said they would fire their boss if they could. Okay, I'm surprised that's so low. Maybe you've got a good boss. I don't know. I wouldn't fire my boss. He's a nice guy. So here we are. 56 out of 300. And they want us to do a 95% confidence interval. In fact, in this question, would you agree pretty much I'm good to go? It should only take me less than a minute to do the answer, right? 56 out of 300, 95% confidence interval. Okay, click in. I'm going to move this over. Right. Remember to make it one sample. And 56 out of 200. Confidence interval, I can't remember now. Let's pretend it was 95 because I can't remember the question. And we hit enter, generate results. And it's that number to that number. So what kind of, they want 3 decimal places, so 0.218. And the upper limit was 0.342. And then they have this little sentence at the end. I've missed these sentences, so I should really do one. Write a sentence or two that interprets this interval. So we are 95% confident that the mean number of employed Americans who say they would fire their boss if they could is within that interval. There's a 95% chance that the true proportion of employed Americans who'd fire their boss falls within that interval. Why is number 1 wrong, but 3 is correct? Because they almost look like the same sentence, don't they? In fact, I should be doing that one, shouldn't I? What's wrong with 1 and why is 4 better?
Because one says true and one says mean.
Yeah. We're not finding a mean. Aren't we finding a proportion? Just some, I almost get caught up. Right. Okay, question 3. Suppose that a survey is planned to estimate the proportion of a population that is left-handed. The sample data will be used in the form of a confidence interval. It says which one of these sample sizes and will give the widest interval. Which one of those 4 would you get the biggest difference between the start and finish number? Obviously, you can't calculate it because there's no, you need more information to do that, but you should be able to figure it out.
Wouldn't it be a small sample size and a evidence interval?
So the widest interval would be a small sample size, so it would be one of these 2, agreed? Now, between these 2, because small samples make the interval bigger, right? You can imagine if you don't know a lot, the interval gets big. And which one of these 2 would be the bigger interval, the 95 or the 90?
the 95.
Because 90 is here, and isn't 95 a bit bigger? So that's a really cool question, because it does get you to think, right? You gotta understand what sample size does, right? A really big sample size tends to shrink the interval, doesn't it? You know more stuff, so the interval gets smaller, right? Small sample sizes make the confidence interval the other way. I like that question. 4. A poll surveyed a random sample of 500 Americans, and how strict your parents are. 33% responded. Okay, 33% of 500. They don't seem to have a lot of imagination. Right, what I've just done in my calculator is found out that that means 165 Americans. So p hat is 0.33, because isn't that 33% as a decimal? Now they want us to do a standard error and a 95% confidence interval. So I'm going to get lazy now and just let Salt do it, right? Rather than do it by hand. So you click in. You make sure it's one sample proportion. And it's 165 out of 500. You do a confidence interval and you generate it. And the standard error is that guy. And the lower and the upper limits are those guys. Do you see how easy it is when you use Salt? Once you tell it what it needs to know, it'll tell you all the good stuff. In fact, there's p hat. So if I went here, the standard error to 3 decimal places would be 0.021. And if I was doing the confidence interval, the lower limit to 3 decimal places is 0.289. And the upper limit would be 0.371. And a really boring sentence, because isn't that the same blinking question that all the other ones tend to finish with? So it's going to be the same answers. Right, in question 5, do you see that we already know the yeses? We already know the sample size. Couldn't we get p hat and the confidence intervals just by going straight into Salt? Can you imagine that these questions are going to be a minute each? Right. Here's another one. Sample size, 185. Oh, 98%. Okay. So that's 185 out of 210. $185 out of 210. And confidence interval, and they wanted 98, which is a weird one to get. There you go. There's your lower limit. There's your upper limit. To 3 decimal places, 829. And on the other side, 933. Any questions about single proportion confidence intervals? Are we comfortable about how to use Salt to get our answers? Anything you're not sure about? Are we good?
Yeah, this is all making sense.
Oh, good. Now, here's a back to front question. Here you have equations without any real details. Nobody knows what that guy is. That's p hat. Nobody knows what that guy is. That's the standard error. And the only guys we've got are 2, 2.58, and 1.654. I know 2 of those answers right off the bat because we did them at the start of today. Remember those magic numbers that you always use? Can you remember what 1.645 would be?
That's 90%.
Okay, I agree. Which one of the other 3 is also one that I used today? And so you should be able to tell me the answer.
99 for D.
Right. Now things get tricky. I have not done a 2, and I have not done a 2.33. Yet somehow or else, whatever, we're going to have to figure that answer out. And they've got a salt up here.
Well, couldn't we just assume? I know that's horrible to say, but since 95 is 1.96, that 2 would be 96%. And that since 99 is 2.58, that 233 would be 98%.
Do you know, I like your logic. And it may end up being correct, but it's not the way I'm going to do it. But your logic is good. Yeah. You're doing a guesstimate, but it's a very reasonable guesstimate, right? I don't think it's going to be that far away. Might even be bang on. So let's do the 2 one. What the heck could that be? Well, it's not obvious how I'm going to get this. I'll show you what I'm going to do. I'm going to get into salt. Going to bring this guy, and I'm going to use the normal distribution, and I'm going to have to shrink this guy down a bit. There, that should be enough. Are you looking again at the normal distribution? Okay. Now, I'm going to do the between, and I'm going to be putting -2 to 2. Now, what you're looking at here is essentially that guy there, right? And I've got a window. I'm going to screw this up. I've got a window in the way of that. And when last time I moved my window, I screwed it up. Right. Do you see this guy in here? That is the percentage of your data that's between those 2 numbers. So 95.45. So if I go back, have I gone and lost my window? Don't tell me I've lost the right one. Where's that question gone? Oh yeah, here we go. Then I have that number before it disappeared. Okay, it's gone and disappeared. You have no idea how many windows I've got open right now. It is scary. Right, 9545. Right, do you want 2.33 standard deviations? Go over here and make that 2.33 and make that 2.33. That's basically where those magic numbers came from. And this time the answer is what, 98. No. 98 and a bit, I guess. How close was that to what you just said? Was your plus or minus 2 95? Is that what you were saying?
I said 96.
Yeah, but look about it. It's darn close, isn't it? It's,
Yeah.
you know, if you rounded it up, well, you wouldn't quite round it up to that, but it's darn close. I suspect that you have to type in nice numbers like 95, 98. Has someone got that same question on? And try those numbers and tell me if that's what they were expecting.
It works. I did it.
Okay, so I mean, you almost nailed it there, and you were just using logic, right? You got one bang on. I think you got the 98, didn't you?
Yeah.
Yeah, and you were darn close to the other one. Right. So I'm wondering now that I've seen that, whether they were expecting you to do what I just did, which is the exact answer, or whether they were just expecting you to do what Brad did and kind of use your logic. You know, if 96 hadn't worked, you probably would have went 95, right? You know, it'd be round about there. So if one didn't work,
Yeah.
you'd have choose the other one, right? Just try to find a question that's a little bit different from all the others, because they're getting kind of same old, yeah. Driving a car's boring, don't want that one. Okay, let's do question 11. It's a very short one. I think this question should have been changed. They should have asked 1,000 American adults and found out what proportion think that there's intelligent life on Earth. Because sometimes I'm not so sure there is, but that's just me. Okay, so it's that horrible decimal guy, you know. What number am I going to be using when I hit salt here? I'm not going to be putting 0.57 in. Agreed?
570.
570.
Right, so I'm going to find 0.57 times 1,000, so 570. So just kick in. Make sure we're on proportions. And do a 570. Do 1,000. Make sure it's a confidence interval and then generate a result, and it's that number to that number. Are we comfortable with that? I think I've probably done as many of that type of question as I want. Would you agree once you've done one, you've done them all? Right? How many yeses? Out of what? Tell me the confidence interval. Salt tells me every number I want, probably some numbers I don't want, and write down the ones they want and call it good. So let's look at some different kinds of questions now. So the first one here says, determine the value of Z star multiplier that would be used to compute an 85% confidence interval. So let me show you how we're going to get those answers. But we need a little bit of theory before we go there. I'm going to go back to a guy that we did at the start. Do you see these magic numbers here? They are called Z star. In fact, they are called a very specific version of Z star. That number there is called Z star 0.90. Or in other textbooks, they don't put a star on it, they just call it that. And that Z star, or the Z 0.9, is the magic number that gives you a 90% confidence interval. So in the same vein, could you imagine that that guy is the 1.96 that they mention here, and that that guy is the 2.58, right, that you do for a 99. So let's try and explain where they're coming from. You begin with the standard normal distribution. It's been a while since we looked at that guy, but can you remember the mean is 0 and the standard deviation is 1, and it looks like that? You remember that guy? Now, if you wanted to, for instance, find this 1.96, what you're finding, in fact, is the number that goes here, and it's positive on the right, and it's the same number on the left. And you want that number so that this chunk in the middle is 95%. So if you wanted to find the 90%, this guy here, you would be finding that between 1.645 and negative 1.645, that chunk in the middle would be 90%, 0.90. So let's suppose that we wanted to find, for whatever reason, a very non-standard confidence interval, because we wanted to. And the one that we're going to go looking for is 0.85, at least in that question 12. So there's going to be a number here, and there's going to be a positive one and a negative one, right? And that chunk in the middle is going to be 0.85. And we are going to find that number. However it is, it's going to go there. So how do we do that? Well, there really isn't an easy way to do it numerically, right? There's not a calculation that you can do that would really be very easy to do by hand. We essentially rely on software, in this case, Salt. Now, because the textbook wants to, do you notice they're just calling it Z star? And technically, shouldn't they call it Z star 0.85? You know, if you want to do it precisely. So you hit use Salt. And I already did that earlier, but now we've got another version of doing that. You make sure you do the between button. Okay. And then you go over here and you put 0.85. Because that's what I want, right? 85. Now, if I scroll down a little bit, you see the picture from there to there, the middle 85. Can you see the number I want? It's here. So 1.4395. And you put the positive. Oh, yeah. Why won't it let me do that? Oh, yeah. Okay, it looks like I'm going to have to type it in, but it's no biggie. I have to delete all this before I can do it.
I think you could just double click in the box. Oh,
Will that make it go away? Well, I've done it now. Okay, so the number that we were using is 1. We did the one 2 decimal places, so 1.44. Right. Let's suppose you wanted a 93%. Right. You want a 93%? Click on that. Make that guy 93. Won't your answer be the magic Z score will be 1.81? Do you know if you wanted a 99.999? What would that be? That would be 99.999% confidence interval, right? The kind of confidence intervals that they might use when they send people up into space, right? Because they really want to be sure that whatever they're doing is right. Okay. That would use a magic Z score of 4.417. Are we comfortable now how you can find the magic Z scores for any unusual confidence interval value? Are we good with that?
I'm sorry. I just tried typing it in and I don't think I did it right.
Was your guy 85%?
No, ours is, well, mine is 75%.
Okay, so in your case, I'm just going to do yours again. We'll check it out. So on this screen, you were 75%. So the number you're going to use is 1.15. Is that okay? Hi, Jade. Did it work?
Sorry, I was on mute. So yeah, so the 0.75, so what number would it be?
The number would be 1.15.
Okay. Thank you.
You're welcome. Now, this guy here is the other way around. If I tell you it's an 85% confidence interval, what's the magic Z-score, right? If I tell you the magic Z-score, which is what the 2.81 is, what's the confidence interval? So I'm back to this guy, but we know the magic Z-score is 2.81. So you go and you do negative 2.81 and you go to positive 2.81. And that's your guy. And what kind of accuracy do they want? 2 decimal places. Ooh, I don't like that answer to 2 decimal places. Check it's 2.81, yeah. Well, if you round it off, it's actually 100%, which I'm not convinced of. I prefer it was 2 decimal places as a percentage. Okay, that's much better. Okay, so that is 99.51. Yeah. Yeah, that I can live with. All right, is there any questions about 12 and 13 before we move on? You know, it's just getting used to where you put the numbers in salt to get whatever it is you're interested in finding. Are we good? Right, so we're moving on to some other stuff. It's going to be perfect timing. My goal is to finish this section. It looks like I'm going to. Here we're being asked to calculate a margin of error, but there is no salt button. That means we're going to have to do old school, right? We're going to have to do it with formula and calculations. So you can't just totally ignore the formula and say, well, I'm just going to use salt every question, because that's not going to be the case, right? So suppose that a margin of error, not that one. Right. For each combination sample size and sample proportion, find the approximate margin of error, right? So it's going to be for a 90, in my question, a 95% confidence interval. And there's 5 questions, but let's just pick B to show you what's happened. In B, N is 600 and P hat is 0.52. And we're being asked to find the margin of error. And there are 2 different answers to this question, which I don't like, but I'm going to show you both. Actually, I might not. I might just tell you the one that I believe is the right answer. At least it's my right answer. To get the margin of error, I first need to find this guy. So kind of way back at the beginning of today, I'm going to use that formula. And that's going to be this fella. Times 1 take away that guy. All divided by, in this case, 600. So if the question was, what's the standard error? I could certainly do that. And the answer I got here is 0.020 to 3 decimal places, because that's what they want. Now, the margin of error. Got it handy? Hope I do. If you multiply this guy with the standard error, that number is called the margin of error. Remember? The margin of error. So I'm going to take, for a 95%er. Oh, does anybody remember the magic number for 95%?
1.96.
Okay. Times the standard error, right? So it's going to be 1.96 times 0.020 and 1.96 times 0.020, and the answer I get is 0.039 to 3 decimal places. And of course, there's going to be some rounding off issues knowing WebAssign. Now, there is, no, I'm not doing it. Sometime I was going to tell you there is another way, another thing. Can you remember the 1 over square root of n, which is the approximate standard deviation? I hope they didn't use that one, because your answer would be 1.96 times that fella. So if somebody's got a version of that, which is question 16? Question 15. Do you want to just do a quick double check on it and tell me, using this technique, was it okay? Was it happy?
Yeah, I got it right.
Okay, so forget about the 1 over square root, and thank goodness the word approximate here is just because they're rounding the answer off. Because sometimes that word approximate has a much more specific meaning, right? The 1 over square root of n meaning, right? And forget it, it ain't happening, so I don't care about it, right? So we're good, right? The way I showed you is the way you're going to do it. Do you see in that question there is no, I guess they do have a salt button, I take that back, but you would still have to do some calculations in salt, wouldn't you? Let me jump into that one then, the 600.52 one, and just show you that salt's not perfect for that kind of question. Oh, the little darlings. Do you see that they're not letting you use the one that I wanted? Okay, even better. Salt button is useless for that question, but I wasn't doing it by salt button anyway. Because when I hit salt, it only allowed these choices.
You're not sharing your screen.
This is the choices you get when you hit the salt button, which are no good. You see, you don't have a single proportion. So I wouldn't even think about using a salt button. You got to do it by hand. In tests especially, try and do as many of these things by hand. You can also do it in salt as a double check. But by doing these questions, I can give a whole load more extra, partial credit than I could before. And I noticed in the midterm there was an awful lot less working than I was expecting or hoping. But I think that was a time issue as well. So that's why you got your extra credit. If you have not done your extra credit guy, do so. You can add up to 20 points to your midterm. And considering your midterm is only out of 100, you could get, as I already know, more than 100%. So don't don't waste that opportunity, right? You get 20 points, it'll make up for the fact, and I believe a lot of you were under pressure with time and couldn't really show me the working or even do some of the questions toward the end. So to try and balance that, I gave you the extra credit. Is there anything else we need to talk about? Because I think we're finished that section. And tomorrow I'm going to do another one where we will do the difference in two proportions, confidence intervals of difference in two proportions, and move on to the mean one. And then on Friday, there'll be one more where we'll do the mean of a single and finish off the mean stuff. And that's all you need to know for up to Sunday. Are we good, guys? Well, thank you for taking time off your very busy day. I appreciate the fact that you came. Hopefully it's been some use to you. And hopefully I'll see you again tomorrow. If it has, I probably will.
All right, thank you, Professor.
You're welcome. I'm going to be doing the officer next, but that means I'm going to close this one on and open up the Zoom meeting for the officer. So if you've got homework questions, just leave this meeting and join the other one. Okay. Right. Bye-bye, guys.
Thank you. Have a good day.
You too.